we talked about fundamental theorem of linear algebra, telling you how all the subspaces of system of linear equations connected. So you have some matrix, you have column space, which are span of columns of matrix A, row space, which is all of the linear combinations of rows of the A. You have null space or kernel, which is all the solutions of AX equals to 0. And then you have left null space, which is all the solutions of X transpose A equals to 0. Okay, so it's like A transpose, kind of null of A transpose. So these are 4 subspaces, and they are connected. First of all, they are pairwise orthogonal, which means vectors which are sitting in one of them do not sit in other one. And they together, like 2 of these subspaces, give you the entire space in that domain, which means that's very convenient kind of way to write vectors as sum of 2 other vectors, okay, from each one of the subspaces, potentially. So you can always write any vector as sum of these 2 subspaces vectors, okay? So you pick one from one subspace, another subspace, any vector X will be combination of them. One of them might be 0, okay? So you don't have to choose both of them together. It might be one or another or both. So it could be all these combinations, okay? And then you map it to other 2 subspaces, which are column space and kernel. And then again, they are orthogonal, and you will have always vectors which are from one or another, or just some of them, but nothing else. So these very important properties, and we're getting back to a little bit easier things that we already discussed a little bit, which is called linear independence of vectors. Again, when we solved some systems of equations, we talked a little bit about independent columns. They're not proportional really to each other. So if you cannot write particular vector in a set, so you have a set of vectors, if you cannot write that each of the vectors as combination of other vectors, linear combination, then the set is independent vectors, linearly independent. So linearly independent practically means that there is no linear combination with non-zero coefficients where you can write particular vector in that set as linear combination of others. And formally you write that way. So you have n vectors, and they are complex or real, it doesn't matter. And you have some constants which are, again, complex or real, whatever they are, depends on your application. In most cases, we'll be using just real numbers and real vectors, but you can define that, yes.
I'm sorry, can we talk about the previous lecture? We talked about the row space, the column space, okay? And in that slide, we see that x equals to xr plus xn. I wonder why x can be, is x always can be represented by xr plus xn, or in some situation yes, they're not.
So this is the theorem that any x, which is that point here, if you can look at the screen, so this point, which is just generic x, whatever the vector is, wherever it is, it always could be written as sum of these 2 vectors, which is xr and xn. But a times xn, which you have here, the derivation of that thing, a times xn by definition is 0, right? So if you're adding a times xn plus xr, you get a times xr, because a times xn is 0. By definition, this is not null space, right? So it has to go to 0. So what you're left with is just AR. But any vector, like no matter what that vector is, if you multiply it by matrix A, you get it in column space of A. Regardless if it is XR, XB, XC, X whatever, okay, any X, it will all go to that column subspace. Why? Because multiplication of matrix by a vector is linear combination of its columns. Coefficients are actual vector, okay? So whatever coefficients you choose, they all move to the B, which is in column space. Whatever the red thing is, all right? Any other questions? So as you can see, like all of the vectors from left go to the B point, which is in the red rectangle. Any vector goes there.
I wonder, can you always find something like x transpose dot A equals to 0, is that such X is always
You cannot do X transpose times X because dimensions will not match. A might be rectangular. Only for square matrix A you can do A transpose times X. So X is n by 1 and A is m by n. So A transpose is n by m. So inner dimensions need to match. The multiplication will be defined. It cannot be m by n inside. So you cannot do A transpose. You can do X transpose A.
Yeah, I say X transpose A.
Okay, so you do X transpose A. So this is left null space, yes.
Can we find such X exist, or sometimes we can?
So sometimes this is only 0, okay? Let's say if A is invertible, a simple example, okay, A is square and invertible, then the only X which will solve that equation is X equals to 0, so it will be only that point where they, both of them intersect, right? So this is that point, like 0 point here, origin, right? And dimensional 0, obviously not number 0, it's like vector 0. So vector 0 will be the only solution, but if A is not invertible, you might have infinite number of solutions to that kind of equation, okay? And then you will have that subspace, which is called kernel of A transpose, which is practically null space of A transpose. That's what it is, okay? And now this might be empty, like that green part might be completely empty, non-existent if A is invertible. But if A is not invertible, this might be some vectors. And all of these vectors will not be here, okay? This is the theorem. This is what the theorem states. These vectors will not be solution of A x equals to whatever. Okay? You will never have that. They cannot be solutions of that system of equations. Which is interesting in itself, that all the left null solutions cannot also solve your system. Okay? So they cannot be solutions of your linear system Ax equals b. Okay. Any other questions? All right, so linearly independent, formally we define that as that weighted sum of vectors v1 through vm equals to 0 if and only if all of the coefficients are 0. Okay. This is the only way when it will be linearly independent. If for example, this is not true, then it will be linearly dependent. And typically, when you have not too many vectors, you can just look at them and say, well, if two vectors are proportional, this is definitely linearly dependent. Because I can, instead of multiplying, let's say you have sum of equal vectors, okay, you have two vectors of the same kind. So you can multiply one by 0, and then second one by some constant, and it will be linearly dependent. So you will always be able to find coefficients which are non-zero and still satisfying that equation. Okay, so it's always possible. Okay, so here's an example. So 1, 2, and 2, 4 are linearly dependent. They should be linearly dependent. Okay, because they are proportional practically. So it's related later. Okay.
It is, so it says they are
So,
not.
so it should be dependent, not independent. Oh, it's not linear. Yeah. I need to rephrase it. It doesn't read right. This is correct. They are not linearly independent, which means they are linearly dependent. Okay. This is what it needs to be. All right. So why is that? Because twice the first one minus 1 times the second one will be vector of 0. So these coefficients are not 0. So 2 and 1, negative 1 are not 0. So I found non-zero coefficients for which the solution is 0. For 0 and 0, it will be trivial solution, right? So it's not interesting. Like obviously, like 0 times the first one plus 0 times the second one will be also 0. So it's not a unique solution in a sense. But I just need to find one solution which is non-trivial solution, and trivial solution is just all zeros. A non-trivial solution exists, so it's linearly dependent. Okay, that's an example. Let's pick another one. So we have vector 1, 2, and 5, 6. They are linearly independent. Why is that? So let's write that linear combination of the vectors. It's some coefficient alpha 1 times first vector plus alpha 2 second vector. You get system of two equations, two linear equations, and solution of that system of linear equations will be by solving that matrix inverse. And since this matrix is invertible, you have only one trivial solution, which is 0. So the solution will be that thing, whatever that thing is, and it's invertible times 0, so it's 0. So the only coefficients which will be alpha 1 and alpha 2 to solve that thing will be 0 and 0. It's linearly independent vectors. They're not proportional. They're not linear combination of each other. Right? Any questions on that? So a few simple rules that you can use to filter out linear independence. First of all, if you have vector of length n, okay, there's like n elements in the vector, and you have more than n vectors, they must be linearly dependent. They cannot be independent. Like more than n vectors cannot be independent. They always will be dependent. So too many vectors is not great. If you have many vectors, they definitely will be dependent somehow. And you can prove it relatively easily. And this works for Cn, for Rn, for all of the spaces, okay? So this is what the first bullet point says. So for any n plus k, where k is larger than 0, it's like n plus 1, 2, 3, 4, 5, whatever vectors in that space of dimension n will be linearly dependent. Okay. Any questions on that? The more vectors you have, more likely you to have some linear dependence between the vectors. Okay, and if one of the vectors is a linear combination of others, or this vector is 0, it's always linearly dependent. Again, practically almost by definition. Pay attention, if you have 0 vector and any other vectors, that set will be linearly dependent. Why is that? Like you have vector of zeros, and then bunch of other vectors, whatever they are, I can tell you immediately that this set is dependent, linearly dependent. Why is that?
Because for whatever coefficient you have, it'll always be 0 when you multiply
So,
by the 0 vector.
No matter what coefficient you choose for the 0 vector, it will be non-zero coefficient because you want to choose non-zero coefficient to show linear independence, right? So you always can show that such coefficient exists, like 5, whatever it is. You pick any random number. 5 times 0 plus whatever coefficients and vectors are, you still get the same result because 5 times 0 is 0 or 10 times 0 is 0, no matter what. You get same result, but 5 is not 0. So it's not trivial solution. So it will be 5, 0, 0, 0, 0, 0, all of the other coefficients 0, okay? So 5 times the first vector of zeros will be 0, plus 0 times all of the other coefficients will be also 0. You summing all of them up, you get obviously 0 vector, okay? So it gives you that first equation, and not all of the coefficients are 0, because first coefficient is 5, right? It's like 5 and other zeros. So any vector 0 will cause any set to be dependent, linearly dependent. This is how you think about that. Okay, any questions about linear dependence or independence?
Yes, so back to the slide. Okay, is n here the number of dimensions and k the number of vectors?
No, n is the size length of the vector, how many elements you have in the vector. K is just regular integer number, positive integer number, 1, 2, 3, 4, 5, natural number practically. It's just for n plus 1, n plus 2, n plus 3, n plus 4, you can pick any number, okay? So if you have more than n, it just says like any number larger than n, which is integer number, obviously. You have linear dependence for any number larger than n. Probably I can simplify that instead of writing n plus k, I just say n belongs to z and larger, or m natural numbers, and then it should be larger than n. Okay.
So, Professor, does this mean that if we were to combine vectors and they were to equal another vector in this set, that would make them dependent?
Yes. If you add an additional vector to the set which is beyond the size of the vector, it always will be dependent, regardless of what these vectors are. These vectors might be, If the vectors are already dependent, then definitely if you add more vectors, it will still be dependent. This is obvious. But let's say you have n independent vectors. So n independent vectors practically span the entire space, which means no matter what other vector you choose, you can write it as a function of all of the previous vectors. This is what next slide is saying. This is what basis means. Basis of vector space. Okay, so you can represent any vector as linear combination of other vectors in that space. And if you have n sized vector, you need only n vectors to represent any vector in that space. Which means if you're adding n plus 1 vector, clearly will be written as a function of previous ones, whatever they are, independent ones. Okay, so what is basis? Basis is defined as set of linearly independent vectors, which span that space, linear space V. Okay, whatever that space is. And it could be like R cubed, or it could be some line in space crossing the origin. If you remember, all the subspaces have to pass through the origin. They have to have zero vector in there. And so it's like linear lines or planes crossing the origin somehow. Okay, so this is how it's supposed to work. So basis means what is the practically minimal subset of vectors using which you can write any other vector in that space as a function of these vectors, as linear combination of these vectors. This is the overall idea of basis. It's, again, we talked about that. You can think about that as system of coordinates. So defining axes, like where each axis pointing. Okay, these vectors of basis are where your axes are, which direction you point. In n-dimensional space, so it's a little bit tricky to imagine in higher than third dimension. Okay, but for like vectors of size n equals to 3, it will be three-dimensional system of coordinates. That could be 1, 0, 0, 0, 1, 0, 0, 0, 1, for example. Okay, it's just vectors pointing into regular standard rectangular coordinates. Okay, so this is what basis is practically. And the idea would be that we want to write all kind of vectors in particular basis, which means in that system of coordinates. That's how you geometrically think about that. Okay, so we have additional definition here, which is called dimension. And the number of vectors in a basis of particular vector space is called dimension. And we write that as dim of V. Again, this definition corresponds to what you would assume dimension is, because if vector length n, dimension is n. Okay. So this is what dimension means, practically speaking. Same thing for other things. And for functions, for example, the dimension is infinite because you have infinite number of points in the function. So infinitely dimensional space. Okay, what are the examples of this kind of basis? So you have standard bases that we discussed already previous time. And standard base is just all of this like 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0 for vectors. Or for matrices, it's like 1 at particular place, zeros everywhere else. And then you have n squared or n by m number of standard values. And again, for matrices, the dimension would be m times n, like how many elements you have in the matrix. This is dimension of the matrix in that sense. For polynomials, you will have standard basis, which is 1, t squared, t cubed, fourth degree, and so on. All the degrees up to degree n, whatever it is. Okay. So for that vector space, you will have these polynomials which are spanning the entire space. So you can write any polynomial as a function of these functions. And practically coefficients of that linear combination will be the exact vector values. So you can represent it as regular Rn vector, right? Just coefficients of the polynomial. And you will have n plus 1 coefficients. So dimensions of polynomials will be not n, which is degree of the polynomial, but n plus 1, because you have also free coefficient. So it starts with 0, right? It's like to the power of 0. So it's from 0 to power n degree. So degree of the polynomial is actually n minus 1 from the dimension. Okay, it's like by 1 smaller than dimension. Is it clear what I'm saying? So the number of coefficients of n's degree polynomial is n plus 1. Take like quadratic polynomial, okay? You have 3 coefficients. But it's quadratic, it's like second degree. 3 coefficients. Free coefficient, x coefficient, and x squared coefficient. You have 3 numbers to describe second degree polynomial. So dimension of polynomial space will be n plus 1 if n is degree of your polynomial. Okay? A little bit tricky, misleading. But that's okay. Any set of n linearly independent vectors in Rn will be basis. Okay, pick any independent n vectors, will be basis of Rn. So you have a lot of freedom of choice what kind of basis you want and how you want to represent your numbers. Practically any rotation, any scaling of the system of coordinates will be completely fine. You can write that completely easily. Okay, matrix rank. So rank tells you how many linearly independent rows in the matrix you have. Okay, and we call it rank. This is the name that we will be using for rank of A, and this is practically dimension of row space of A. But interesting property here is that number of linearly independent columns is exactly the same, always, regardless of the matrix, which is very interesting theorem. I would say unexpected, surprising theorem, that number of linearly independent columns is exactly as number of linearly independent rows, regardless of what your matrix is. Rank is always the same for both. Okay, so this is what this theorem is stating. So rank A equals to dimensions of row space and equals to dimensions of column space. They both are equal always for any matrix. And pay attention, let's say you have matrix, I don't know, 500 by 2. Your rank cannot be larger than 2. If your 2 columns are linearly independent, which means they are not proportional, you know that your rank is 2. You don't need to compute 500 rows. Doesn't matter. Everything above 2 will be already dependent. Okay? Because each element in the row will be 2 elements, 2 elements, 2 elements. And you know that if you have more than n vectors, you will already have linear dependence. So everything which will go beyond the first 2 rows will be dependent on the first 2 rows. So you can write any vector out of this 500, 498 as a function of the first 2, as linear combination. Okay, any vector. Or if they're independent, like any vector in R2. Any vector with 2 elements. Okay, because any 2 independent vectors of size 2 will span R squared. Entire thing. Okay, so you'll be able to write any vector as a function of these 2. This is how we define rank. And this is why I want to go back to that diagram that we had, just to show you something on the rank and dimension. So pay attention, the dimension of row space by definition is R. How many independent rows you have. But since this one is complementary to that subspace and total number here is n, so the dimension of that space must be n minus R. They complement each other. It's like how many vectors you have in one basis versus how many vectors you have in another vector, in another space, subspace. So this should complement that sum of that dimension, and that dimension should add up to n because you have total n here. The vector length is n, right? So number of vectors and bases here should be R. So here it will be n minus R, whatever complements to n. Here, same thing. We just showed the theorem that column space has exactly same number of linearly independent columns as you have linearly independent rows. So this will be also R. You don't need additional number for that. It's still number of independent rows. Okay, all columns. And then total is M, which is a vector to which you map. Okay. So this dimension of that kernel of left null space should be M minus R. This is how we compute number of vectors in the basis that you need for the second part. Any questions on that? Yes.
So does the null space or the left null space, do they also have their own basis vectors?
Yes. Each one of the subspaces will have their own spaces which are not interacting and not overlapping with the other subspace above it.
And then what are those?
They will be complementary, I would say. They complement the vectors which are bases above. So you cannot represent any vector in kernel A from the basis of row space A, okay, or vice versa.
That is why they are orthogonal.
They are orthogonal, that's what it means, yes. They are completely independent subsets of vectors, do not intersect. Right? Yes.
I want to make sure that the column space of A, its dimension is R because
Because of the theorems that we just showed.
B equals A XR, and XR is dimension of R. Is that correct?
Sure. Any other questions? Okay. So this is about matrix rank. Here is example. For the first matrix, you can find rank. What do you think is the rank of the first matrix?
3.
Will be 3. By 2.
First row and third row is dependent.
So you have first row is proportional to the third row, which means the rank cannot be 3 already. So it can be 1 or 2. But are all the rows proportional? So second row you cannot really write as a proportional to the first row, right? So rank should be 2. So you have 2 linearly independent rows. How about the second one? All right. It's also 2. Why? Because you have 2 linearly independent columns, right? So it must be 2. They will be proportional to each other, it would be 1. Both of them would be 0, then it would be 0. Okay, so additional theorem, yes.
Is there a case where the rank of that matrix could be 3?
True. Invertible matrix.
It's an invertible matrix.
Here is a theorem which is stating you what is full rank. Full rank is like order n. Let's say you have square matrix A, n by n. Okay. So all the following things are equivalent for matrices. Number 1, it has full rank, which means rank of that matrix is n. It's equivalent, which means if and only if A is invertible. As if and only if determinant not equal to 0. And this is why we have the property that matrix is invertible for determinants which are not 0. As if and only if columns are linearly independent, if and only if rows are linearly independent, if and only if when you're doing like row echelon, this Gaussian elimination, you get all of the full form, which means all of the pivots which are not 0. This is what it means, okay? Later you will see that this is also equivalent to not having eigenvalues 0 and many other properties, okay? All of them are equivalent to having full rank. But if one of these properties is not true, okay, it does not mean that you can calculate rank somehow out of it. So this is a more tricky question. Like if it is full rank, you have million of different properties, you just measure determinant or whatever other thing, it will tell you like, yes, it's full rank. But now if I'm asking you what that rank is, you will say n. You don't need to compute anything. If it is full rank, it's n, has to be. But now if it is not full rank, like what is that thing? Then you need to solve system of equations to compute all of this, how many coefficients you get non-zero. This is much more headache to identify rank of the matrix, but you have just comment rank in MATLAB and it will tell you what rank of your matrix is. You don't need to struggle with that. Typically it's done through Gaussian elimination and you count in the number of pivots which are not 0. In the row echelon form, whatever it's called. But again, this is not part of that course, so I'm not even going into this technical computations. It doesn't matter for us really. how you compute that numerically. Any questions on that? This is the most important part of that lecture, and in a sense, it's generalization of dot products. And all of the signal analysis, or almost all of the signal analysis, is based on that. Okay, and if you read professional literature on signal analysis, you will have a lot of that kind of symbolism and that type of theorems and assumptions that you already know that by heart, all of that stuff, and you can manipulate it in your head somehow easily, and you see like where things are coming from. But these things are not that easy. They're pretty complicated and not obvious, really. So it's, again, I hope to devote entire course to things of that kind on even easier levels than that math level, just with more intuition, more like where things are coming from and what you can do with them, because that's important for that case. So we define some new function, which we'll call inner product, and the definition of the inner product will look like that. So we'll have those, how do you call that kind of brackets? Angular brackets. Okay. So using this angular brackets between vector x and vector y, and this function is producing some sort of scalar out of these two numbers. Okay. So this scalar will be called inner product of x and y, and always think like about dot product. Dot product is a good example of that inner product. Okay. So it's like x dot y practically, because all of these rules that we are talking here are x dot y types of rules. So, and I'm defining that already for complex variables that will be generic enough, but you can think about real ones as well. So first of all, you have left linear property, which means you have that linearity of the left part of that inner product. So if you doing ax plus by dot z, you get the distributive laws of this like alpha times x dot z plus beta times y dot z. This kind of scalar times the first dot product plus scalar times the second dot product, whatever it is. So it's like linearity property of dot product in a sense, but this property works also for inner products in general. Conjugate symmetric property. So second one is if you flip in the order. So for dot products, we haven't even discussed it because we talked about real functions, but here you need to take conjugate of that if you switch in the order. So for complex values, for real values, it will be, you can just switch the order. Okay, so x dot y equals y dot x for real values. But for not real values, it will be conjugate of that value. Okay, if you switch in the order. So it's not, you cannot switch the order without changing something if it is complex. All right. And then positive definite property. And we will talk about positive definiteness a lot when we talk about matrices, positive definite matrices, which are very important in controls. But here it's a little bit different, but property is very similar. Property says that inner product between x, and think about that as x dot x, which is practically norm squared, right? Because this is what x dot x is, how we define norm. It's dot product between vector to itself, square, like square root of that. It's larger than 0 for any x which is not equal to 0. And technically it will be 0 only when x equals to 0 vector. All right. So it has these three properties which are defining inner product. And as you can see, dot product is one of these inner products. It's just generalization for other kinds of vectors, because we will need that for functions, for example. And how do you define dot product of functions? It's tricky, right? It's not that simple. So here are properties of inner products. Again, same properties as we've seen for dot products. If you're doing inner product with 0, you get always 0, no matter what. So inner product of x with itself will be always positive, and will be 0 only if x is 0. And also second part, which is linearity of second part, will be same thing, but with conjugate. Because the bar at the top means conjugate. Remember what conjugate is? Just a minus bj in complex numbers. So second, like imaginary part becomes negative. You kind of flipping it upside down with the real axis, all of the upper numbers becoming negative numbers. So because of that property, okay, of that property, second property, this will be true. So you'll have to take the first coefficient conjugate and second coefficient conjugate. Again, if they are real, you don't care, because conjugate of real numbers is the number itself. So it will be linear with regard to the second coefficient as well. So it will work for real numbers and real functions. It will be fine. Okay, but if you have some complex stuff, then you need to put conjugate to make it consistent. Any questions on that? Yes.
Show this the conjugate symmetry property by kind of like a proof or some example.
So what you have is something like that. So have the rules that x vector x, vector y, inner product equals y x. That's that, right? So we are saying something like that. So we have now x alpha y plus beta z. So this equals to alpha y plus beta z x, right? So to make it, so this will be alpha y plus beta z conjugate x, everything is conjugate, okay? It's complex numbers. Now for that we know that this is linear, which means that conjugate of these multiplications, you can separate them into separate conjugates. Okay, and now you have linearity here, so it will be alpha times y x plus yx, yes, plus beta conjugate times z conjugate x conjugate, which will be equal alpha conjugate, and then you replace this one with the conjugate on that thing. So it will be going backwards from here. xy beta xz. Okay, so I'm using this thing backwards. Switching, when switching the order, I can remove that thing. All right? So you get to that theorem that this needs to be conjugate and this needs to be conjugate. Okay, so norm is defined by the square root of inner product of x and x. Same thing with dot product, right? So we define it exactly the same way. This is called canonical norm because it's defined by the inner product. And then two vectors are orthogonal as we define for dot product if their inner product equals to 0. And this will work for orthogonality of particular kind, because now you can define different inner products, and orthogonality will be pairs that inner product, and they will be called also like inner product spaces in linear algebra. So you can define different things. And one very important theorem that is used a lot in practice is Cauchy-Schwarz theorem. Again, we mentioned that for dot product, but this is true for any inner products as well. So if you have absolute value of inner product, whatever your inner product is, it's always smaller than multiplication of norms of the components. This is how Cauchy-Schwarz works. All right? Any questions on that?
what really makes, so I think my question is, why do we need a special definition for inner products when we have dot products? And just
We will see that in a second why we need other types of inner products. Because, like, look, dot product will not work for matrices, for example, but you can define it for matrices. And some people, like, look, some people do not even use the word inner product, they just say dot product, while they mean inner product. So dot product, it's formality, right? It's like what name you give to a particular thing. So I want to differentiate between dot product and inner product, because dot product I will be using only for vectors, but inner product, it's much broader than that. You can apply it to matrices, to functions, to polynomials, to whatever, any kind of vector spaces, okay? So this is kind of more generic name, similarly as you say, you can say number or you can say scalar, okay? So in linear algebra, people are using the word scalar all the time, but scalar is just number. So they do that to differentiate between matrices, vectors, and all of that stuff, and just numbers, okay? Just number. You still can say number, right? But numbers are also in vectors and elements of vectors, matrices, and so on. So people say scalar to identify something which is sitting outside of the vector, multiplies vector by scalar, or matrix by scalar. It's just name. Yes.
Can you explain the left linear property? Because I'm still not sure why it looks like that. Left linear property.
So think about dot product, okay? So in dot product, you are doing element by element multiplication,
Yeah.
and then adding them all together, right? So if you're multiplying first one by some constant, let's say, okay? So let's separate that into two separate properties. You can write that linear property as two different properties. Homogeneity, which is multiplication by constant, will multiply the result by the same constant. And also addition. If you're adding two inputs, the outputs also will be added. Like if you're thinking about that as machine, which is taking two vectors and producing some number, okay? So it has that machine, which is taking x, y, and producing some output number, which will be the dot product or inner product. So if you multiply the first coefficient by 5, let's say, okay? Like you have inner product or dot product between x and y, like x dot y, and you're multiplying x by 5, which means all of the numbers in that vector scale by 5. Is that the same thing as not multiplying by 5, but multiplying these two vectors first, and then multiplying the result by 5? Is that the same thing? Sure. Let me write it. Okay. So, space. So what happens is, let's say we are checking that property, okay? You have, let's use dot product, okay? So be simpler to see. So have vector x, which is x1 through xn, vector y, which is y1 through yn, okay? Generic vectors, whatever they are. And you have dot product of x dot y multiplied by some alpha. This is that thing, okay? So it's like alpha x y. So what is that dot product? So it's alpha times x1 y1 plus xn yn. Something like that. This is dot product, right? So you can put that alpha anywhere here inside. So you can put it multiplied by x1 through xn, or multiplied by y1 through yn. You can put it anywhere inside, right? It will be like regular algebra. You can move that number anywhere you want. So this is the idea that that thing is equal to that thing. Associativity rule of dot product. Why? Because it doesn't matter where you put alpha. Also, it's same thing as x dot product with alpha y. Okay. But in the case of inner product with complex alphas, you will have to put that thing here. This is a difference. It's not really difference, it's like how dot product is supposed to be defined in the first place, but we haven't defined that before. So I ignored complex numbers at that time. Probably I should start working with complex numbers from the beginning, but practically last time I saw that thing used with that thing, well, maybe like one application out of millions. It's very rare, but we're actually using complex things. You have a little bit in electromagnetics and you have some of it in Fourier transform, but other than that, we do not use that much that rule. But this is what it is, okay? This linearity, homogeneity, okay, part of linearity. Now you need second thing, which is saying what happens to x plus y z, which is x plus y dot z. Okay? This is a superposition rule of linearity. So what happens is you have distributivities like x dot z plus y dot z. Why is that? Because x plus y is vector x1 plus y1, x2 plus y2, and so on, xn plus yn. This is a vector. And now dot product with z, which is z1, z2, zn, which is x1 plus y1 times z1 plus xn plus yn times zn. Right? This is what it is. But this is exactly that thing, because you can open parentheses. This now it's regular algebra now. Okay, everything is scalar. So it's x1 times z1, x times z1, xn, zn, it will be x, zn. So all of them will be just opening parentheses and you will get that. This is linearity property. So this is superposition, homogeneity, it's equivalent, like both of them together, equivalent as alpha x plus beta y, z, whatever, equals alpha x z plus beta. Linearity property. And we will see that all of the linear operators satisfy that same property. What linear operators do you know? Have you heard about linear operators? Calculus. Old stuff. The linear operator is something which is practically satisfying that type of rule, which is saying that if I multiply my input, like it's something which is taking multiple inputs, single input, doing something to that input and returns some sort of other output. Okay, it could be vector, number, whatever it is. So linear means that if I will multiply my inputs by some constant, the output will be multiplied by exactly the same constant. And this is what we have in linear systems. This is what we will have in all of the linear algebra stuff. Like it's just becoming proportional. The output becoming proportional to the change of the input. Okay, so k times input, you apply some function to it, you get output multiplied by the same number. So this is homogeneity property. And second property, if you're adding two inputs and measuring two outputs, the outputs of each one of them separately will be added as your output, which means you're sending one input to the system, you get one out. Sending x1, getting y1. Sending x2, getting y2, okay? If you're sending now sum of two inputs, which is x1 plus x2, you get one y1 plus y2. This is superposition rule, right? And this, like in electrical engineering, we're using that a lot because we send one source and measuring the output of the circuit, and then we turning off all the other sources and turning that source on and measuring that output. And then we turn all off, turning that one on and measuring output of the system. Now, if we turn all of the sources on, the output of linear system will be just sum of all of these outputs that we measured before. Right? This is how superposition works in linear systems in general. This is the same idea. Linearity means that you can modify output by doing something proportional in the input. Right? This is the same idea. Other questions? Okay. So as I mentioned, dot product is very simple example in Euclidean space, and we'll talk about Euclidean n space, which means vectors of length n. For simplicity, Rn or Cn will be a dot product. And we define that only for R, but you can define that with conjugate if you have also C. This one will be very important space because we will work mainly with functions. And functional space is called Hilbert space or continuous functions on interval AB. It's closed interval between number A and number B, whatever it is. And that space is called Hilbert space of continuous functions. So these functions will be from some interval AB, where you'll have some inputs, and to some complex or real numbers, whatever they are, regular functions. Right? So for them, you can define inner product like that. So between function f and function g, which is integral on interval a to b, of the first function times conjugate of the second function, dt. Each one of them function is time, or whatever the variable t is, could be space also, or something else. So pay attention that if both of them are real functions, you don't need the conjugate, it's just multiplication of two functions and integral of them. Integral and multiplication. So it's kind of generalization of dot product for functions. And people are using that, and this is basis for most of the integral transforms. This is where integral transforms are coming from that inner product. And you'll see a little bit why this is connected somehow. You have also same thing for matrices, it's called Frobenius inner product. And this is defined as trace of A conjugate transpose times B between matrices A and B. Remember what H means? It's conjugate transpose. You transpose in the matrix and making conjugate on each element in the matrix. Okay, this is the superscript. And if the matrices are real, it becomes even simpler than that because conjugate of real matrix is the matrix itself. So it will be A transpose B. And what is A transpose? Trace of A transpose B. Trace of A transpose B is all elements pairwise multiplied and summed. It's like you're thinking about each of the matrices long vector, that you're putting all of the elements in one long vector of the matrix, and you're doing dot product between them. This is what it is. Okay, so it's kind of parallel to dot product for vectors, just element by element. All right, this is that Frobenius inner product that we are talking about, dot product between matrices, if you wish. But you have many more other definitions for same things, for different other inner products, for different vector spaces. So now we move, do you have any questions on the theoretical part before we move to the applications? Yes.
When you say the Hilbert space, the integral is ft by g of t bar. What does that bar mean?
What part?
G of t
Conjugate.
conjugate.
Conjugate. So bar above it is conjugate, which means if you have complex function, the function might produce complex numbers. So the result will be conjugate of that result. So imaginary part will have minus sign, that you will invert the sign of the imaginary part of the result of the function. Because function will produce numbers as a function. Like complex functions you cannot draw because you have two components. You have real component, and you have imaginary component, like a plus bj part. So the b part will be negative b, so it will be a minus bj for that function. And a and b will be function of t as well. each component will have their own function of t. So it will have also phase, angle, radius, and angle in polar representation. Okay. So this angle will be just inverted upside down. Again, we probably will not see any complex functions except Fourier transforms in signal analysis, which is one of the most popular transforms. So it's good to know how it works, I guess. So here is an example of ECG noise removal using linear subspace projection. And we'll talk about projections to linear subspaces. It's all will kind of come up together to the same formula eventually, but we'll get that as example first. So do you know what is the difference between EKG and ECG? It's cardiography. It's heart measurements, electrical heart measurements, ECG, electrocardiography. But some people call it EKG, not ECG. Why EKG?
Is kinesio like muscles? Or?
No, EMG, muscle is M.
Oh, there's one.
EMG is for muscle. Myography, electromyography, it's for muscle. But people call like electrocardiography, some call ECG, some call EKG, and you have that in literature, people using two different words. K is from German name for cardiology. So cardio, but in German starts with K, not with C. So since EKG was developed originally in Germany, they used EKG. So everywhere in the world, people started to use it EKG. But when they translated that to English, it became ECG. But the original name was EKG because cardio in German starts with K. Historical. Oh. Okay, but we will call it ECG. Okay, British pronunciation. So we have a lot of problems with cleaning that type of signals, and especially you have all kind of problems with outside line power noise, which is 60 Hertz, and affects all kind of channels unexpectedly. You don't know like what phase you have to that signal, what amplitude you have to that kind of signal, and so on. So it might be a problem, right? You don't want the problem to appear. You don't want all these ripples of 60 Hertz in your signal because you want to identify all kind of properties of your EKG signal or ECG signal. Okay, you want to identify all kind of specific waves, R to R intervals, which is between the pulses. If you've seen how it looks like, I can show you like how it looks like. It's the top part. It's ECG. Okay, this is the clean ECG. So you want to get that kind of ECG and not noisy ECG, obviously, to detect all kind of shapes and patterns. Now, we want to remove 60 Hertz noise from it, which is coming obviously from power line. So how can you do that? And this is very special noise because we know that it's always 60 Hertz, okay? We don't know the amplitude, we don't know the phase exactly, like how it is shifted compared to your recorded signal, because you start your recording not synchronized with the outlet, obviously. So how would you remove that kind of signal? You can filter it, you can use notch filters, which is filtering particular band of frequencies around 60 Hertz, like from 59 to 61, for example. Very narrow filter, which is kind of killing that particular frequency. And people are using that a lot in all kind of biomedical signal analysis processes. They just kill 60 Hertz, 120 Hertz, all the harmonics of the 60 Hertz, okay? Because typically you have also other harmonics. But our approach here will be a little bit different. No filters whatsoever. We don't need any filters. The idea is that we know how the noise look like. And if you know that, we can take that signal, which will be noisy with that 60 Hertz, as you can see, we just added 60 Hertz here, and it looks pretty horrible. And all these peaks are kind of destroying some other peaks on the way. And I want to get back that kind of signal, which is very clean signal. So the idea is that this is how it's supposed to look like. This is the original one. This is added with 60 Hertz oscillations. Pretty big amplitudes as SNR is not great. Signal to noise ratio. And here I want to get that one without any filtering, using just linear algebra. Right? Just linear algebra. So the idea is to take that signal, and this signal is living in some sort of complex subspace. Whatever that space is, we don't know that space, but we know space of noise, and this is the key point here. We know that the noise is 60 Hertz, and it will look like some combination of sine 2 pi f0 t, and f0 is 60 Hertz, and cosine. So why is that? Why is it linear combination of these two functions? Because you know that sine is shifted by 90 degrees versus cosine, okay? So they are shifted versus each other. So their linear combination can write practically these particular coefficients, can write any sinusoidal wave of any amplitude. Okay, so with alpha times sine plus beta times cosine, you can write any sinusoidal wave with any phase. This is trigonometry, okay? So it's like you have omega t plus phi plus some angle inside the cosine or sine. So you can get any phi by modifying these coefficients, all right? This is trigonometric rules, how you can apply it. So the idea is that linear combination of sine and cosine can describe any sinusoidal wave, whatever it is, including sine, cosine, and everything in between, like shifted to any time point, okay? And any amplitude, because you can multiply these coefficients by any number, you will get all kinds of amplitudes. So it will be alpha and beta, okay, multiplying sine and cosine. So this is the subspace of our noise. Practically, this is basis for our noise. So any noise of 60 Hertz could be described as linear combination of sine and cosine with that particular f0 frequency. Okay, this is what we know about the noise. This is how it is. It was defined by these properties. Okay, so the idea is, first of all, to project your given noisy signal into noise space, which means what are the closest noise components that you have in that signal. What is projection? Orthogonal projection. It's perpendicular, which means the closest one, like perpendicular, right? So you're dropping it into that subspace to get the closest result, which is without noise. You have that subspace, which is whatever complicated subspace of signals, and the noise is orthogonal to that signal. So project it to your signal space, and you will get only signal. You will not have any noise. This is the overall idea, okay? And now we will see how we actually get there. So here's how we will not do all of that today, but we'll start explaining how you do projections to particular column spaces. If you remember, previously we discussed how to project one vector onto another. Remember that? So we had x transpose y divided by x transpose x, which is like dot product divided by dot product, times that vector will give you projection onto that particular vector. Here's the same thing, but now we have, instead of single vector, we have entire space. And space is described by span of all of the basis vectors. And we will put all these basis vectors as columns of matrix A. All right? So here's what happens. We want to project given vector y, whatever that vector is, into column space of A, which is all of the linear combinations of columns of A. And you can think about it as practically basis of your vector space. All of these columns, organize them as columns of A. All right? So geometrically, here's how our problem will look like. Let's say this is that subspace that you want to project to. Right? This kind of dotted line, it has to pass through origin. It could be one-dimensional in that case, or it could be multi-dimensional, but I cannot draw it in multi-dimensions. So I'm using a very simplistic example here. So that might be, for example, plane crossing zero as well for more dimensions, or hyperplane for even more dimensions. Again, I draw it, so using just blue line as subspace, example subspace. Now you have that vector y, which is red vector, which is noisy signals that you have. Okay, so it's some point in that n-dimensional space, okay? You want to project it, which is an orthogonal drop on that particular subspace. That projection will generate error vector, which is the smallest possible vector from that point y to that subspace. And this is why it is orthogonal. Orthogonal means the shortest distance. In that sense, okay? smallest norm of that error. This will be the overall idea how you project different things. So here's what happens. You have the py vector, which is a projection operator times y, and you want it to be, should be linear combination of A columns, right? Because this subspace, the dotted line, is column space of A, which means it's linear combination of columns of A, which is some combination of A. And you want to find that py to be that linear combination of A. So it will be A times some sort of vector of C. This is what linear combination of A is, remember? So coefficients in vector C will be those coefficients of like by how much you need to multiply each column. Is it clear so far what I'm doing here? I'm just writing generic combination of columns of A as A times C. This is linear combination of columns of A, practically speaking. All it will be, okay, for particular given C, but I don't know what that C is so far, okay? I want to find P such that if I will multiply it by Y, which will do that projection, it will be able, I will be able to describe that vector as linear combination of columns of A. This is the overall idea where I'm going, is that like what I want, okay? But P needs to be some sort of matrix, so it's linear transform of that vector. And I will write that as just some sort of K matrix on the right multiplied by matrix A. So it's like A times K, and K I want to find, because AK will be matrix of the same dimension that I want for P. Okay, so I'm looking for such a matrix K that what will happen is PY equals AKY. So A times K times Y will be exactly the same thing like my projection. Right, so I'm looking for that kind of K, whatever that K is. And this matrix is to be determined. We don't know what that matrix is. But what we do know, that this is orthogonal projection. And for orthogonal projection, this error should be minimal. Okay, what does it mean that error is minimal and the projection is orthogonal? This means that this vector is orthogonal to this vector, perpendicular to this vector, which means the dot product between this vector to this vector should be 0, which means that dot product between each column of matrix A to that vector should be 0, right? This is what orthogonal means. We learned that for vectors. So thinking about it like vector by vector, each column of matrix A will be multiplied, it will be orthogonal. So here is what we do actually. So error, which is y minus py, do you understand why it's y minus py? So this one minus this one will be that error vector. So y minus py will be error vector, okay? Must be orthogonal to all columns of A, which are spanning that kind of subspace, which means that A transpose times that error needs to be 0. Why is that? Because what is A transpose? You flipping A and rows becomes columns and columns becomes rows, right? So it's first row of A times column of error. Means it's practically first column of A, dot product is error. And this needs to be 0, needs to be orthogonal, right? You impose in that orthogonality on each one of the columns of A. So taking now A transpose row is A column. So it's A column times vector. We will talk about it next time more, but just imagine this practically every column dot product this vector of error will be 0. So you'll say that this is equal to 0 at the end, okay? And the idea is you open in parentheses here, you get A transpose Y minus A transpose A K Y equal to 0. So you can move that part on the right side with opposite sign. And what you get, you can solve it for K, okay, that equation, matrix equation by inverting that matrix. So you'll get solution of orthogonal projection. Okay, so your K will be that thing. All right, so I want to correct something from the previous lecture, as I was notified that we have some problem with one of the formulas that I proposed. So that last formula that you see on the right side, linearity, is obviously incorrect. Okay, so when you're doing inner product between x and alpha y plus beta z, it looks almost the same as linearity on the left component of that inner product, but we just conjugate to the coefficient. So it should be x with y and x with z, and not x with z and y with z. Okay, so this part here, here. So this is x with y and x with z, and not x with z and y with z. Okay, so the correct one will be very different. So let me correct it here. So it will be x with y, x with z. Okay, this is the correct one. And the only change is that these coefficients need to be conjugates instead of regular coefficients with regular linearity that we saw here. This is without conjugates, and then it is linearity on the right component. This is his conjugate because of that. And I showed on the board like computations that I did, development of the formula on the board. The development was correct. I did on the board. I actually solved that on the board, and the question that I got on the board was correct one. This one. Right. Any other questions? The previous lectures? Yes.
Could you give us an example of conjugate function in the integral?
Conjugate function?
Yeah. So,
Okay.
not
So
sure.
it's already a few conjugate functions. In complex number conjugate function, you're just taking a particular function which is a G that be minus A, and you go to conjugate, it will be A minus BG, whatever the coefficients A and B are. But you can do the same thing in complex plane with radius and angle, which is polar representation coordinates. So e to the j theta conjugate with e to the minus b theta, which means practically it means you are not changing the radius, but you are changing the angle. And rectangular coordinates, any point real imaginary or okay will be just reflected with regard to that axis. And this is conjugate of this point, and this is conjugate of this one, and this one is conjugate of this one. And it's just reflection with regard to real axis. This is what conjugate is. You're just reflecting it here or other way around. Depends. So let's say if you have some point which is, I don't know, or 3, you will get minus 3. So from 4 plus 3j, here, the point which is minus 3j. That's conjugate. Right?
So if it's a time function, it would be like exponential of j omega t, and it transformed to exponential minus j omega t.
J omega t, yes.
Okay.
You're just changing the angle because this was your original angle. You're changing that to that angle, which is practically minus theta. Whatever the theta is, it could be omega t, it could be 5, it could be whatever you want. It's just j times whatever. All right, so this angle becomes negative same angle because this is just reflection. This all happens.
So is it always reflection on the x-axis? So if
Conjugate is always reflection on the x-axis. Yes, same thing here. I mean, you have some point here, for example. You have that kind of thing. You'll have it here. So that angle will be reflected here. Same angle, just negative. Okay, going into opposite direction. Other questions? All right. So I want this time to go through the example more specifically through subspaces, and then we got to orthogonal projections. Just to remind you that we talked about linear spaces. Then we said, well, you can represent vector as a function of other vectors, and this is idea behind million of different signal processing, machine learning, you name it. So we want to represent one vector as a function of some other vectors. And typically these vectors we will call bases, and basis is kind of minimal subset of vectors which is spanning entire space. of interest or subspace of interest. So you have particular subspace that you want to be your answer to be in that subspace, all right? And you can write any vector in that subspace as combination of only a few vectors. And how many vectors do you need? It's exactly the dimension of that subspace. This is the number of vectors that you need in the basis of the subspace to represent any vector subspace, which means if you want to represent some vector in three-dimensional space, you need three vectors. Okay? If you want two-dimensional subspace, two vectors are enough. Any linearly independent vectors in 2D will give you basis for the R squared. All right? So you can just pick any independent vectors. Now, we also talked about how great it would be to have all these vectors orthogonal to each other. Because we think about that as a basis as system of coordinates. Okay, so these are defining axes of the system of coordinates. And rectangular systems of coordinates are very convenient compared to that kind of systems of coordinates, angular, where you have angle between the axes and then you have some sort of overlap. You kind of squeeze in some parts of the space in particular ways. All right, so this is the idea of why we want it to be rectangular. It's not necessarily rectangular, it doesn't have to be. But now we will see some properties of what that orthogonal or perpendicular means in terms of vectors, not only for regular vectors of linear algebra, but also for functions, let's say, and for other things. Because all of them you can represent in linear spaces. Polynomials, functions, matrices, vectors, it's all from the same theory, okay? And you can apply exactly the same rules, similar kind of inner products defined for them, and so on. So it's very convenient that you have that general theory of everything in math, in linear algebra, okay? In physics, we are still looking for theory of everything. Math, we found it. Here it is. Okay, it's all about projections, orthogonal projections into particular subspaces. All right, it's a theory of everything in linear algebra. So maybe we should use board, that will be more convenient. I will use a board and we will develop that orthogonality principle and get to a few important formulas here. Okay. Okay, so let's say we have a particular matrix A. And this matrix will be rectangular, doesn't have to be square. So A will belong, let's say, real matrix of M. Okay. And we want to project particular vector, which we will call Y. We'll limit that to real numbers, but we can do the same thing with complex numbers. But to make that projection work, we need it to be size M, dimension M for that vector. Why? Because we want to map it with matrix A. So matrix A columns, we want to write we want to write Y as a linear combination of columns of A. And since column length is M, so each one of these vectors needs to be M. So sum of vectors of length M will be still length M. So this needs to be length M. Okay. So what I want to write is projection. I go like that. You have axis here. You have some vectors that you want to project to particular subspace. Let's say this is our subspace. If you remember, the subspace need to cross the zero here. And I'm showing only simple example, geometric example of that. And this is subspace of whole space A. So columns of A make use that kind of subspace. It could be like hyper surface somehow, hyperplane, right? In multiple dimensions, but I'm drawing just single line as example. Okay. And now you have some vector, which you will call vector Y. And we will have projection of that vector Y into that column space. This will be orthogonal projection, which means this one is 90 degrees. That's what we want. Okay. So we want that thing to be also vector. So this will be vector, just pointing to that point, and this will be projection of vector y on that subspace of columns of matrix A, whatever that subspace is. Right? So we are looking to find that py. What is that p? Projection operator to project it into matrix column space. This is a goal. Okay. So I want, and obviously not every vector will be sitting on that line, right? So you will have some sort of error here. Let's call it E. This vector will be error vector. The difference between real y and its representation in that particular subspace. They are different in most cases, unless this vector is already in that subspace. Okay, not every vector you will be able to represent as sum of columns of A, right? Not always, depends on the matrix A. For example, if the vector is like n and matrix is n by n and all of the columns are independent, then you can represent any vector in that subspace because this is entire n-dimensional Rn, right? So you can represent any vector. So it will all sit on that, so you will have entire space covered. But some matrices are lower rank, so you cannot represent any vector in n dimensions here, or m dimensions in that case. So it will be some sort of projection, but you're looking for the closest one. Like you're thinking, well, I need the closest solution. And we will return back to that multiple different times in multiple different ways. Because when we will be talking about least square solution, this will be exactly the same idea. You're looking not for exact solution because exact solution does not exist. So you have system of equations which is self-contradictory, let's say. So you don't have any solutions, like no solutions. But it's overstated. You have too many equations in the system of linear equations. You want to find solution which is producing minimal error and not exact solution because there is no exact solution. The idea will be how you minimize that error. You're doing that kind of projection. And I will see that from completely different perspective when we will talk about least squares solutions or systems of linear equations. You will get exactly the same formula as we will develop now. So this is kind of a completely different angle of looking at things, but you get exactly the same answer with least squares. So you practically get to something which is called Penrose inverse of matrices or pseudo inverse of matrices. And this is where it is coming from, like all that idea of pseudo inverse matrices that you cannot really invert, but you are doing like you can invert it. Like what is the closest inverse that you actually can do? Like what is the closest matrix to invertible in a sense? This is the idea, okay? You just projecting it to a particular subspace first, and then you inverting it where you can. But I'm jumping forward a lot just to give you overall picture where we are going with that. All right. But for now, all we want is to find projection operator, which given any vector y, by multiplying by that vector y, and p will be some sort of matrix. Okay, multiplying by vector y, you will have something which could be representable exactly as a linear combination of columns of matrix A. This is the goal. Okay. So here is what we have, and I will use some kind of a little bit tricky notation. But here's how I will write it. So py equals some coefficient c1, constant, scalar, okay, times first column of A, I will write it as A1, like that. Okay, the symbol like column of A, first column of A, right? So far, is it clear what I'm drawing here with all these lines? It's like column, taking first column of A, plus C2, second column of A, plus E, and total you have n columns, A n column A. So this is the representation that you want. You want that there will be some coefficient C1 through Cn, multiplying columns of A, and this is obviously linear combination of columns of A, such that P times Y will be written that way. This is what you want. Okay, so far? Okay, so you're just representing that thing. Now you can write that thing as A times vector C. That vector C will be 1 through Cn. Remember how you multiply matrix by vector? This is one of the ways. It's just linear combination of columns of A. Okay, so you can write that as A times some sort of vector. And you don't know that vector yet. All right, we will need to compute what that C is. But you know that Py equals A times something, whatever it is. So you don't know P, you don't know C, you know A. But you want that this somehow will work. Okay, so you can represent that thing as A, and you need that P to be matrix, right? So to be matrix, you introduce in some new matrix. That C will be some matrix times Y. Because you know that on the right it needs to be multiplied by Y somehow, and on the left it needs to be multiplied by A. So there is something in the middle that you don't know and needs to be determined. So matrix K needs to be determined here. Right? And then in that case, based on these definitions, P will be equal K times A times K. Okay, so this is first formula to remember. And we don't know what that K is yet. We just know that this is some matrix A times some other matrix, whatever that matrix is, matrix K. All right, so far? Any questions? So P equals to AK, all right? So for orthogonal projection,
So we're saying that matrix K times Y is equal to vector C, right? Well,
AKY equal KY equals to
is-
C, yes. KY equals to C, yes.
so the matrix times a vector.
The matrix times vector will be vector of the same
Yeah.
size, yes. So we just need to find what that K is. We don't know it yet, okay? But we will use orthogonal projection. So what we know is that this vector is perpendicular to this vector, to the error vector. Okay, so error has 90 degrees, and this is the shortest distance between Y and that subspace, because it is orthogonal, perpendicular, all right? So what needs to happen is that A1, which is the first column here, column, right? So product with E should be what? 0, orthogonal. A2, same thing. Dot E is 0. And so on. A and N. N. Dot E equals 0. So all of them 0. So what is E? How can we write E? So what do we know about E? How can you write that as a function of Py and Y? So what we know is that this vector plus this vector equals this vector, right? So we can write that Py plus E equals Y. Okay, regular algebra, vector algebra. So we need to find what the E is. So from here, E equals Y minus Py. This is second thing we need. Now, how can we write that entire thing as a single formula? What is dot product of multiple columns with some vector E, whatever that vector is? This is a vector. Remember how you write dot product? How you can write that as multiplication of matrices or vectors? It's transpose times the second vector. Transpose of the first vector times second vector. So since columns of A, so this is how it will look like. It will be A transpose times error, which is Y minus Py. Which means what you do with A transpose? you convert columns into rows. That will be first row times that vector E, which is exactly that first dot product, right? So it's like first column dot arrow. Second row in the transpose matrix will be second column of A, dot product is E, and so on. So it's like same thing practically. And you know that this thing needs to be vector of 0, and dimensions will be, this one will be n by 1, this will be m by 1, this will be n by m. It's like rotated matrix. So dimensions switch here because of the transpose. This is the same vector as y, so it's like m by 1. And this is vector of zeros, which is length n, because multiplication is n by 1. All right, so far. So let's open that and see what happens. And from here, we practically need to find k. This is what we are looking for. We want somehow to use that thing to find k. So let's simplify that a little bit. A little bit of algebra for practice. Okay. So get A transpose y minus A P y equals A transpose y minus A P. I will replace with AK because I want to find K. Okay. That will be minus A transpose P. P will be AK. All right, y equals 0. Right, so far.
A transpose y minus A transpose py or A py.
So it's A transpose, a distributivity law. It's A transpose y minus A transpose py. So this is P.
She means in the,
Like
at
maybe
the
you
first,
the first half,
where it says A transpose
A-
y minus A py.
the
Shouldn't be A
second one
transpose?
minus
This
yeah
one?
it should be A transpose.
A transpose. Okay. Thank you. All right. So you get something like that. And then you want to find K somehow. So let's simplify a little bit more. So have A transpose A K Y equals A transpose Y. Okay.
Should be negative?
So no, I'm moving them on the other side. Okay. So I have equal between them now. Okay, so this one equal to this one. So this one should be somehow equal to this one. Those two matrices. So I need to find K such that that multiplication will be somehow A transpose, whatever it is. Okay, so I don't know K yet. So how do we solve that type of equations? Matrix equations. I need to get rid of that part somehow. I want K on the left side and something on the right side, which will be formula for K, obviously. What do you do to get rid of that one?
By on the both side.
Cannot divide in linear algebra.
Or
Inverse,
inverse, yeah.
yeah.
You multiply by inverse of that matrix. So what you do, you multiply on the left by A transpose A inverse. This is what will happen. So you'll have A transpose A inverse times A transpose A. You can cancel out, obviously. A equals A transpose A inverse, A transpose.
Y is-
That's it. And you can multiply by y. Okay, so this cancels. So this is I times k, and I times k will be k. So from here, k will be equal to A transpose A inverse A transpose, right? And from here, equals what? From there, it's just A multiplied
times that.
by that thing. So it will be A transpose A inverse A transpose. This is our projection operator. And this is also least square solution to that problem. And also in like pseudo inverse of A. Have many different names for the same thing. This is the idea. This is where you get with it. Okay, so if you multiply that matrix by Y, you will get something in column space of A. Questions on that? So you need to remember that formula. We will return to that formula multiple times in this course. Popping up in all kinds of places and applications. This is least square solution of the million of different problems. Everything least squares is that formula. Okay. Questions? Okay, now we can get back to our idea of signals and projections to the spaces. Now when we know the answer to the problem, we can actually share that again. Okay, so this will be the solution, and this is what that thing is saying. Get the formula at the end, hopefully the same formula, right? Yes. Same formula. Okay. So you get the projection operator, which is allowing you to project any vector from m-dimensional space to subspace of columns of A. And now what we do for, just to remind you what was the problem. The original problem was to have some sort of signal, and now you know what kind of noise you have in that signal, and that noise was like 60 Hertz line noise, which is added, and you don't know the phase of that noise, you don't know the amplitude of that noise, but you know that it's sinusoidal, and you know that it is somewhere in the signal with particular amplitude. So you have some power of that noise, in a sense. And you want to get rid of it, which means what you want to do is to project to the subspace of noise and separate that subspace from everything else. Because you don't know how the signal subspace looks like. It's like complicated, depends on the signal. But you know how the noise would look like. So you want to project to that subspace of noise, sines, cosines type of thing. And then you subtract from your original signal that subspace of noise. You get signal. Practically, you're thinking about signal as signal plus noise. You're computing the noise, which is at 60 Hertz sine, and then you're just subtracting that. So what would be the projection operator directly to the signal space now instead of noise space? So this will be like if you're taking like sine and cosine as columns of matrix A, then you will get projection to the subspace of noise. Okay, so you'll have only noise component, which is only 60 Hertz sinusoidal wave with particular amplitude and phase. But what would be the projection operator that you can get for signal out of that? What it should be. And as I said, signal is just original Y, which is noisy signal, minus noise. So what happens is you need to subtract it from I, matrix I, identity matrix, that operator to get the final operators that you actually need. And let's see why. So here's how it goes. So you have that ECG signal, and you have 60 Hertz noise, and we say that our basis functions are sine and cosine of some kind. And this is because you can write any phase of sinusoidal wave with weighted sum of these two functions. Okay? And you have the constant frequency, and we want to project it into the orthogonal noise space. So we talked about that. And here's your matrix A now. It will be rectangular, obviously. So you doing that noise basis, you just put in sine waves for different t. You have like long, very long matrix A with two columns. Okay, yes.
I'm not really sure whether the question is a question for this topic, but you're saying you can write any sinusoidal in form of sine and cosine. I mean, if this is the case, then why do we sometimes have to use Fourier transform and use a complex sine and cosine coefficient?
So Fourier transform, are you talking about Fourier series or Fourier transform?
Yeah. Fourier transform, I mean, multiplication of the signal by the complex exponential.
Yeah, so Fourier transform gives you entire spectrum of the signal, which means all the distributions of all of the possible frequencies on continuous scale, which means for each frequency, you'll have particular magnitude and angle phase. All right. here you know that you have only one sine wave with one phase and one frequency. You don't need Fourier transform in that case because now you know particularly what your noise is. In Fourier, typically you don't like people using Fourier because they don't know what is the spectrum of noise or spectrum of their signal. And typically they go other way around because they know more about signals than about noise. Right? So in most cases, you don't know what your noise is. You assume it is like white noise, maybe like broadband, or you assume this is some particular pink noise or shot noise, or it depends on physics of the problem, right?
Yeah.
So you assume something on the noise, but you don't know much about noise. In that case, this is the other way around. You know everything about noise, and you don't know anything about signal.
Yeah, so I think my question is for this one. We are assuming the basis vector for the noise we know.
Yes.
It's sine and cosine. So the noise can be represented as a linear combination of sine and cosine, right? Yeah.
Yes.
So the question is if that signal can be represented as a linear combination of sine and cosine, this is kind of rare, like sine and cosine. So why do we sometimes have to represent some signal using?
You're asking generic question, like why people use Fourier transform, and then Fourier transform always as a basis is sine and cosine, or complex exponent, which is still sine and cosine, just in complex domain.
Yeah.
Sinusoidal waves.
Why don't you?
So here's the thing. So it's not only sine and cosine. Typically, Fourier transforms are used for periodic signals or something that you assume to be periodic, which means it repeats itself at particular intervals, right? So Fourier theorem states that any periodic continuous signal with additional properties, okay? So you have not any, almost any signal which is periodic and continuous could be represented as infinite sum of sines and cosines. So you can divide it into multiple sinusoidal components, if you wish.
Okay.
Now, similarly, you can do the same thing with polynomials, for example, which is called Taylor series, where you can say, well, any continuous differential function could be like smooth enough, okay, like nicely behaving function, could be written as sum of polynomial, as polynomial practically, approximated by polynomial, and the approximation be as good as you want. So you can always find polynomial which fits practically all of the points of entire differentiable function in particular interval, and this will be your Taylor series, all right? And you have many more different series, not only that kind of polynomial, you have Hermite polynomial representation, you have Laplace representation, you have Lagrange polynomials, you have all kind of, all right? So sinusoidal, it's just one out of possible bases, okay? You have many more bases. And sometimes you're using sine times exponent. Let's say Laplace is just regular exponent with st, okay? So you have all kind of bases for all kind of transforms. They just show you different perspective on your signal or your data somehow. So Fourier transform specifically gives you information about spectral content of your data. If you care about spectral content, which means like how much of the 20 hertz I have in my signal, like, or how much alpha band, like brain waves, like 10 hertz or whatever you have up to like from 8 to 13 hertz. How much of that I have in my signal? How strong is my alpha frequency band in my brain signal? Like to see like if you're kind of semi-dreaming or closing your eyes, which is increasing significantly your levels of alpha range. So in that kind of case, you want Fourier transform on that, or something similar to Fourier transform, to see what is the content for that range of frequencies, because this range is important for something that you investigate. But sometimes you want polynomial expansion, sometimes you want some other expansion, exponential expansion. You have all kinds, right? And we will talk about some of it. We will talk about Fourier series. We will talk about sampling theorem, which is also doing expansion in terms of function, which is called sinc. If you know from algebra, sinc is like sine divided by x, sine x divided by sine pi x divided by pi x, something like that. So it's a sinc function. And you're doing expansion using these functions. And these are the best functions to reconstruct signal back from discrete signal to continuous signal. Depends on the goal. But yes, people use a lot Fourier transforms because people are interested in frequency domain. That's what it shows you. Any other questions? Yes.
So if the signal is not periodic, then we cannot use Fourier series to represent it.
No, you can't. For non-periodic signals, you need to use Fourier transform. Then it will work. Fourier series is only for periodic signals. It needs to repeat every period. Right? Okay, so you have all these functions, and you're using P noise projection as A transpose A inverse times A transpose, as you see on the board there, right? And then signal projection is just Y minus the original noise, okay? And noise is P noise times Y. It will be I times Y minus P noise times Y. So I times Y will be just Y, and P noise times Y will be just noise. Subtracting from the original signal, noise signal, and you get your signal. That's it. So clean signal will be just projection into that subspace of signal. Any questions on that? This is overall idea. Now we will move to MATLAB code, which is actually doing that.
So equals to 1 minus P noise.
So it's, are you asking about the second line of the bottom?
P signal equals to I minus.
I, identity matrix, minus matrix P of noise.
Why is that?
So here's that. So you get, so Y clean, I don't know how to label it, equals Y original Y, which is noisy Y, minus Y noise. Right? So we discovered already that Y noise is P noise times Y. Right? Now the dimensions of P noise, this matrix, right? So this matrix is, what dimensions of that matrix are? What is the projection? What should be the dimensions of P noise? This multiplies vector Y, so the second dimension must be what? M. Okay. So what kind of matrix is that? M by M. Matrix.
Okay.
Okay. Now, you cannot subtract. You want to do something like that. You want that this thing will be equal to something minus something times Y. Okay. So the second thing will be P noise. So what is that first thing? You cannot, like, it should be one practically,
yeah.
right? It should be one, but you cannot do one minus matrix. There is no sense to do one minus matrix. Okay, so one in matrices is identity matrix, okay? It will be I times Y, which is still Y, same thing here. And this will be P times Y, which is that Y noise. Noise times Y, okay? So this operator is practically P signal. I minus P noise. Multiplying P signal by Y, which is that thing times Y, will give you Y clean. All right? This is the overall idea. So you have the formula coming from there. Let me share it again. Okay, and this is where this formula is coming from, that I minus P noise. So that P signal times Y will be that clean ECG, whatever it is, and we saw the result already will look like that. Okay, so this is the Y that you have, Y signal, and this is cleaned ECG after you multiply by that operator, which is practically the same thing as the original signal. In signal. So here's how you actually do that in MATLAB. All right, so you load in that ECG sample, which is ECG map, and this sample is given in any MATLAB distribution, so it's kind of built in to MATLAB, so you don't need to download anything. You can just open it as is. And let's say sampling frequency is 500 Hertz, 500 samples per second. And then you can define time for that entire signal based on the length of that ECG vectors that you have, which would be whatever from 0 to the last sample minus 1, y minus 1. Because indices in MATLAB are 1, 2, 3, 4, 5. So length will be not starting with 0, it will be starting with 1. But you want the time to start with 0. So time will start with 0 seconds, right? And then it will run from 0 to n minus 1 sample to get exactly the same number as in the vector. And then you divide it by sampling frequency to get it in actual seconds, right? So time will be in seconds because what we represent here, this plot is seconds, okay? These are seconds. All right, so you have the time vector, you have sampling frequency, you have ECG signal, which is that ECG variable, all right, which has all of these values of jumping pulses from cardiology. And then we add some random angle to our line noise. We choose some random variable here, and it will be some number between 0 and 1, whatever it is. Multiplying that by 2 pi, so it could be any random phase from 0 to 2 pi. Okay, random distribution, uniform. You pick particular phi, which means it will be cosine of particular amplitude, actually sine, and random phase, whatever that phase is. Each time you'll get different answer, okay? Just to make sure that it works for any kind of angle, okay? That kind of procedure. So here's what you do. So you define that angle phi, and your noisy signal, which is our y, okay, will be ECG, which is that original clean signal, plus amplitude of 0.5. And if you noticed before, the overall amplitude was of the spike of the R peak was 1, about 1. So it's like almost half of the magnitude of the original signal. Very strong noise, half of the amplitude. So you're saying this is 0.5 times sinusoidal 2 pi ft plus that random angle phi. Okay, and then you added that noise to your original ECG, and you get your Y signal, which is noisy Y. Okay, so far that's what this code is doing. It's just generating synthetically your noisy signal, which you see in the middle part of the plot. This is that noisy thing. If you plot that noisy stuff. Okay, now you build noise spaces, which are 2 pi ft, and t is that vector that we defined here for all of the variables that you have, and cosine 2 pi ft, right? 2 columns. Now, our projection matrix, as we defined at the top of the board, okay, it's I. In MATLAB, it's funny function I. So they do not say identity, they say EYE for the identity matrix. It sounds like I. They like to joke about things. Of length t, which means practically how big your matrix is, right? How long your matrix is, minus A times A transpose A inverse A transpose, that formula, okay, projection formula. So this is our P signal, and cleaned is P signal times noisy, that's it. Now you plot all of these three. So you plot the original signal, which is ECG, you plot the noisy signal, which is our Y, and then you plot the cleaned signal, cleaned ECG, which is that final thing, and you get that plot that I showed you before. That you can replicate that entire thing, that entire experiment. All right, and you can play with the angle, you can play with the amplitude, you can play with whatever, it still will work fine for any of them. It doesn't matter what you choose, any sinusoidal way. But try to do that if, for example, this is not 60, but 62. What do you get? Like, will it be cleaning it or not? Or how much it will be cleaning? Or maybe not at all. Maybe making it even worse. So pay attention how this works. You can play with this kind of code and see what happens. Any questions? Yes.
Why not just define a variable t? Why we need t equals to?
That variable?
Yeah.
So you define that as vector of time in seconds. Just instead of, you can use samples, it doesn't matter, but this is just, ECG is typically measured in seconds, like it's time scale. So you're recording ECG in time, and 60 hertz needs to be on the time scale. So 60 hertz is 1 divided by 60 seconds, right? So you need everything in the same units. To make it in the same units and to make sense out of 60 hertz, because otherwise you need to define like what is 60 hertz in samples using just time 1, 2, 3, 4, 5, 6, 7, and so on, like indices. This will be just different number. It will not be 60 anymore. It will be like what is hertz in samples, right? Hertz is 1 divided by second. Clear? So when you're saying you have 60 hertz, you need to know how many samples within one period. And this is why you convert everything into seconds, and then 60 becomes just 1 divided by second. Everything in units of seconds. Simpler to compute.
Is it like a specific time frame?
Yeah, it's specific time frame. They give you, I don't remember how many seconds, but they give you, the vector length is 4 seconds. Okay, this is 4 seconds, you see. Time is from 0 to 4 seconds. There's 4-second recording of ECG. So you define that exact vector of 4 seconds here. So this will be from 0 to 4 seconds. Maybe 3 seconds, dot 9999, whatever last element is, but approximately 4 seconds. Right? Any other questions? Okay, so to summarize what we've seen here, how you deal with different kind of problems like that. So noise lives in known subspace and signal is very complicated subspace. And then you can use just basic linear algebra without designing any kind of filters to remove that noise if you know properties of that noise. This is important. You need to know exactly what subspace this noise lives to clean up that subspace completely from your signal. Otherwise, it will not work. If you don't know anything about your noise, well, that kind of technique will not help you. You need some sort of filtering of other kind. Now, general method is just you identify noise basis, like sine, cosine, or whatever your type of noise is. It would be rectangular noise, for example. I don't know, whatever it is. Construct projection matrix, and then you just apply it to data. And you get noise alone, then you subtract in that noise, and you get the original clean data. And you have many more applications of that same kind of thing. It's used in canceling interference, in communication systems. It's used in like removing motion artifacts or beamforming for EMG, not EMG, MEG, which is electromagnetic caps that you put on head. Sensor arrays where you have multiple microphones recording some kind of audio, and then particular things which are coming at particular phases at particular timing to different microphones, noise coming at different angles and distances and so on. You have multiple different applications to the subspace projection ideas, but this is not as popular as signal expansion, which is again holy grail of entire signal processing. Like entire signal processing is based on that idea, which is again not that far away from projections. So we still do orthogonal projections and we still do representations of vectors by other vectors. That's what it is. So here's the idea. You want to represent vectors in orthogonal basis. And we talked about that a little bit before. And you want to write, given a basis V1, 2, 3, 4, 5, whatever of that particular subspace that you want to represent it to. You want to write vector x, which is your given vector, in that system of coordinates. So these vectors are coordinates in a sense, and you want to write it as coefficient times first vector plus another coefficient times second vector plus linear combination of vectors as usual. Okay, and you can represent that as a, like if you think about three-dimensional space, it will be some vector x, we will call it signal, and could be even infinitely dimensional space if it is continuous function, for example. All right, so it can have infinite number of coordinates, which is like all the dots on the curve. And then you want practically to find all of these coordinates alpha 1, alpha 2, alpha 3, which are just coefficients in that expansion of the vector in that particular basis. Now, you can think about all of these values as projections of that vector onto that vector, right? You're just projecting them perpendicular projection or orthogonal projection into these basis vectors. That's it. And here's why. Here's how can you think about that. You just take on both sides of the previous equation inner product with VI, and let's see what happens. This is a trick, okay? Basis trick for all of them. So what happens is you're taking inner product with X, so you replace that square by X, all right? And you get inner product with VI. So it's X, inner product or dot product, whatever, is VI. Okay, this is what you have on the left. On the right, you replace that square with that entire linear combination. Remember that? So this will give you that kind of thing. So you'll have A1, V1 with VI, A2, V2 with VI, and so on until you get to the last one. Okay, homogeneity property, practically this is coming from linearity of the inner product. All right. Now, look what happens when you do inner product between Vn and Vi where they are not equal to each other, two different vectors. And the vectors are orthogonal, which means dot product between each vector to another vector, but not itself, is orthogonal to that vector. What happens to the dot product or inner product? 0. So practically all of them are zeros except one, which is when you have Vi with another Vi here, okay? Whatever that I is, so I is some running index, it could be 1, 2, 3, 4, 5, whatever, but it's like only one out of that entire sum, whatever that thing is, and it will be AI, alpha I, Vi with Vi. But what is alpha I, Vi with Vi? Alpha can go out, right? Like you can take component out because of linearity again of the inner product. You can take alpha out of that inner product. That's one of the properties that we learned about inner products. And then you get inner product of Vi with Vi. But this is exactly norm squared. This is how norm is defined. The dot product between X and X is X norm squared, right? So this is alpha times Vi squared norm. Questions so far? What we want to find actually is alpha I. Coefficients, right? Like what are the coefficients here? That's what we want to find. So look at that equation. So X dot Vi equals alpha I square of the norm of Vi. This is what we know. So you can compute alpha I. Now all of them are numbers, right? This is number. Remember that inner product or dot product is a number, it's scalar, right? Norm is also scalar. It's just a number. It's not vector. It's number. Alpha is also number. So it's like regular algebra here. You have one number equal alpha I times another number. The formula will be alpha I is that number divided by that number. That's it. Okay. So this idea is practically basis of all of the signal processing. That kind of formula. That you can compute these coefficients just by projecting to each one of these vectors and normalizing by norm. Okay? Just dividing by norm of that basis vector. And it would be great if that basis vector would have norm 1. It would be even more convenient. And this basis is called orthonormal basis, not orthogonal basis, but orthonormal basis, which means every single vector in that basis has norm 1. So in that case, you'll have even simpler thing like that. Okay, so if each norm is 1, then X, which is the original vector, you will be able to write that as linear combination of vectors Vi, and the coefficient of that linear combination will be just inner product between X and that particular Vi. That's it. As simple as that. So this is why it is so convenient to have rectangular system of coordinates, because all of these terms just fall, cancelled. You don't need them. With non-rectangular system of coordinates, you will have all of these components, okay, other components, projections to other things, all right? So it will not be orthogonal anymore. So you will not be able to write that thing, that equality. And then it becomes much more complicated to compute. You will need to design separate functions for things, but this is only half of the crazy deal here with signal analysis, okay? This is just one direction, like how you go from representation of X to these coefficients, but you need also to go back somehow. Let's say you have that representation of that vector, and you have these coefficients, how do you go back to vector X? So in that case, you can go back like that, and it's kind of simple. But in multiple other cases, it's not that simple, especially if it is not orthogonal, and especially if it is not orthonormal. Okay, sometimes you need additional work to do to find function which is taking you back to the original function, which is, by the way, that function is also called dual function. If you see or hear somewhere in literature that people are using term dual function, this is dual function, the projection to that particular component. And we will see a little bit more of that. Any questions on that? Or we move from simple vectors to functions and doing that for actual signals now. So this was kind of introduction how it works with regular vectors. But now, if you remember, we defined also inner product for functions, which was integral from 0 to t, particular AB interval, whatever, of the first function times conjugate of the second function, t whatever variable is, right? This was the idea of just generic inner product between two different functions. It's just integral of multiplication between them, in a sense. And this is where all of the Fourier transforms, Laplace transforms coming in, all of that stuff, okay? Again, remember that formula, okay? Memorize it. This is important and this is important, the blue things, because this is what we will be working with, okay? Just remember that coefficient of that expansion in the basis VI will be just projection, which is inner product with that particular vector. That's it. For orthonormal spaces. If it is orthogonal spaces, which are norm 1, you also need to normalize by that norm squared. Okay, so we want to represent vectors and signals in more convenient form. Typically as a function of all kind of analytical functions or something which is simple to represent, okay? And in Fourier series, for example, it will be sine and cosine again, or exponent of j, theta, whatever functions. And we will show that they are orthogonal first, all right? So it is possible to represent a signal in infinite number of ways. So you can write it as linear combination of all kind of in all kind of bases, with all kind of functions. So it's not a big deal. You just need to pick one which is convenient for your purposes. So in practice, typically you use simple functions, simple analytical functions like exponents, sine waves, polynomials, that kind of functions, because they are easy to deal with and also have some practical intuition behind them, like how they look like and what it means to have particular frequency. And we will use them as building blocks for the expansion of our signals. All right, as I mentioned, dual functions are just the formula for computing the coefficients of that expansion that you have. And coefficients, which is that inner product, is just projection, which means what is the closest point on a particular vector, which is as similar as possible to your particular vectors that you are projecting it to. All right, this is the idea. So you kind of comparing how similar your vector is to each one of the basis vectors. Almost like correlation method. For orthogonal basis, the dual functions will be the basis functions, which is extremely important property. So you will have exactly the same function up to a constant. It might be multiplied by constant because sometimes you need to, if it is not orthonormal, you will need to divide by norm squared, okay, to make it same. But the type of the function will be the same. And this is why you get it, like if you learn signals and systems course, you get Fourier transforms, for example, as magic. Here is the formula, you have that exponent here, and wow, magic to compute coefficients, you have exactly the same formula, just times coefficient, like 1 divided by t. This is the difference between computing coefficients and computing the actual Fourier transform, okay? inverse Fourier transform, practically same formula, just conjugate all the bases. Remember that? Like you have e to the j, whatever, and the inverse Fourier formula is e to the minus j, same thing. Same formula. So this is dual function. And this is why, because this e to the j, whatever, are orthogonal to each other. This is a property. And also in inverse Fourier transform, you will have 1 divided by t coefficient in the formula when you compute in the coefficients. Why is that? Because t is norm squared of the exponent, and we will develop that hopefully today, maybe, where it is coming from. So here is an example of Fourier series, actually, complex Fourier series. You want to write any function as sum of sinusoidal waves of some kind, and this periodic function, and period would be t, and we will call that signal or function s of t as a function of time, all right? And we will have orthogonal basis functions which are vk. So we want to write that as linear combination of these functions, and these functions are also function of integer number k, 1, 2, 3, 4, 5, plus minus 0, all right? So this will be 2 pi divided by t, and t will be t periodic signal. So 2 pi divided by t is like 2 pi f, it's like omega angular velocity, if you learn that in physics or signals, and times kt, this is regular basis that you use in Fourier. And then we want to represent that signal as linear combination of that kind of functions. These coefficients c1, 2, 3, 4, 5, plus minus. All right, so far, this is what you get as Fourier series. Like when you learn Fourier series, they tell you, oh, can you write that as that way when vk is that thing? This is complex Fourier series from signals. Okay, so let's see why in the formula which you get here, you get also 1 divided by t for the inverse Fourier transform. Okay, because this is how the inverse Fourier transform will look like. Exactly the same thing, but you need to divide by t. Remember something from signals and systems long time ago, probably. But if you look in any formulas, you use t, and funny thing about that thing, that sometimes people do not use here t. People use something else here in Fourier series. You have 2 ways to define Fourier, not 2, many ways to define Fourier series. And this is what many of my students making mistakes. They just look online and use wrong formulas for it, because we define in the course formulas in that particular way. And sometimes people just define that as 1 divided by square root of t here, and 1 divided by square root of t here to get exactly the same function for inverse. So forward, which is computing the coefficients, and inverse will be exactly the same function. This function will be orthonormal. You're just normalizing by square root of t, because squared norm is t, so the square root of t is norm. Okay, so if you divide here by 1 divided by square root of t, and here divide by 1 square root of t, you get exactly the same function, forward and backward from Fourier transform. All right, so here's the idea. Here's how you get it. Just to see where it is coming from. Relatively simple computation just coming from properties of complex numbers. So you have that vk as exponent of j pi divided by t k t, right? So you want to compute what is that vk norm squared, by which you need to normalize that thing to get orthonormal vectors now. So this will be inner product between vk and k, obviously. And it will be integral from 0 to period t, vk dt. This is the definition of inner product between vk and vk itself. So this will be equal integral a squared. Because if you remember from complex numbers, if you multiply number by its own conjugate, you get absolute value squared. Any number times that thing equals alpha squared. for any complex number. Okay. So this will be, yeah, from 0 to t. This will be integral from 0 to t. Absolute value of exponent j 2 pi t k t. The value squared dt. But what does that say? What is absolute value of exponent to j whatever theta? Like it doesn't matter any angle. It's always one. It's unit circle, right? These are just angles on unit circle. So this one. So this one is integral from 0 to t on 1 dt. Regardless of what is here. Doesn't matter for any k. Which is, what is that? Integral of 1 on interval from 0 to 1, from 0 to t. Remember how you compute that? You have 1, 0 to t, 1. Area of the rectangle. Okay, this is what integral is. Area of rectangle here. So it's t. So norm vk squared equals t, which means that you need to divide these vectors by t to get them normalized. Okay. Now, if this one is square norm, to divide it just by norm, it's square root of t. Right? This will be the norm of v. That's it. This is the idea. And doesn't matter even which one of them, because all of them are the same. Any k, doesn't matter what k you use. Same thing for all of them. Right? And this is where this formula is coming from. You need to divide that by t, which was exactly the formula that we saw here. That formula. Okay. So that coefficient will be that inner product divided by that norm, which is in that case t. Right, for any vector. Any questions on that? And again, if you would use, oops. Yeah, so this is where this t is coming from. Okay, but again, you can define that as square root of t here and square root of t here, and it will be already orthonormal basis. So we will continue talking today about signal expansion as one of the examples for linear spaces or vector spaces. And I brought already some examples and representation of vector in orthogonal spaces. We have orthogonal bases, everything cancels out, you get very nice formula for coefficients of that expansion of vector in particular basis. And then if it is orthonormal and not only orthogonal, it's even better because you don't need to divide by norm of that vector of the basis. Okay, so practically the coefficient will be equal to inner product or dot product between your vector and basis vector. That's it. Very simple formula. Now we had that motivation for representing these vectors as like basis, and then we started the example of Fourier series, which is one of the examples, but you can think about many other examples where the basis function is a little bit different. So Fourier is one of the simplest ones because it's orthogonal. It's very convenient. It's not orthonormal. But if you divide it by square root of t, then it becomes orthonormal. If you do instead of vk equals to exponent of the formula that you see on the screen, you can use 1 divided by square root of t exponent, same thing, then it will become orthonormal. And we showed previous times that practically vk with vk inner product will give you t. So vk with vk, if you divide that by square root of t, it will be t divided by square root of t divided by square root of t, which is practically 1. So from that definition, you know that this is orthonormal basis for any k. right, regardless of what coefficient k you choose. And what I promised previous time that we will also show that this is actually orthogonal basis, because I haven't shown that, I just claimed that. I said like, well, all the exponents are perpendicular to each other, but it needs particular proof, and this is not difficult to prove. So here's how you do that. So why the basis is orthogonal? You have the function which is vk. So vk will be an exponent to the j to y divided by t, k, t. So this is the basis function, right? For different k's, you'll have different vectors, different functions, right? So what we want is inner product between vk and v, let's say m. K is not equal to m now. Or any other pair of vectors, all right? Which is not the same vector, just different vectors. So this is what you want to compute. What do you want to get here for orthogonal basis? What to get if it is orthogonal basis? 0. You want that inner product to be 0 between any pair of vectors which is not the same vector. Okay, because this basis is orthogonal, so every dot product between each one and the basis should be 0. Okay. All right, so let's see what that thing is. If you remember, this thing is integral from 0 to t of vk, vm, dt. One of them obviously is a function of t, function of time. All right, so far, this is definition of inner product between two functions. So this thing will be integral from 0 to t exponent of j to pi divided by t, which is period of the function kt, times e, and I'm replacing k with m now. And to get conjugate, you need to put minus here. Right? This is how you do conjugate in polar coordinates. Same thing, 2 pi divided by t, now it's m, t, dt. Yes.
So what is the bigger picture here?
Picture.
Yeah.
So I'm trying to show that this basis is orthogonal, which means that all of the exponent functions are perpendicular to each other based on the definition of inner product. And this will tell me that I actually can use that formula that I used before. If you remember, for computing the coefficients, it's just inner product between the vectors that you have or functions that you have and basis function.
Yes.
Otherwise, you have all kind of other components. You remember we had like big sum in linear decomposition of that vector. We had multiple different inner products, is all of the basis functions, but they need to cancel out, all of them, if it is orthogonal. If basis is orthogonal, which means you're representing it in orthogonal basis, all of these components fall out. So to compute the coefficient, all you need is like single inner product instead of n inner products, right? Simplifies life. So I'm showing that this is actually orthogonal, which means I want to show that this dot product between vk and vm will be equal to 0 always, regardless of what k and m are. So here's how it works. So I'm multiplying that kind of thing. So this integral from 0 to t, exponent j 2 pi divided by t, k minus m, t. Remember rules of the exponents when you multiply exponents. This is just sum of the powers. Okay, and since this power is negative, so I need to subtract that. So this will be something like that. Okay, so let's compute that integral. So integral of exponent of something is 1 divided the power times same exponent, right? So this will be like that. So it will be 1 divided by power will be t divided by j to y m minus m. Is the coefficient like 1 divided by power of exponent. And same exponent, which is j to y divided by t a minus m when t runs from 0 to t. That's it. Regular integral. So how do you compute that? You put, first of all, t here instead of t, and then you're subtracting when you put in t equals to 0 here. All right, so these are two components. So regardless of what that thing is, what is the function when t equals to t? Just put here t. What it will be. So this t will cancel with this t. Right, so you'll have j to pi times some integer, whatever. But what is j to pi some integer? It's like 2 pi times 1, 2 pi times 2, 2 pi times 5, 2 pi times million, whatever. So think about that as a circle, right? So it's 2 pi angle, which is 0 angle practically. So it's a real number, all right? If you multiply it by any constant, it's still 2 pi something, okay? So it's still 0 angle, it's the same point. It's actually 1, regardless of what k and m are. Right? So that entire thing is 1 for t equals to capital T, okay? What happens when t equals to 0? So it's 0 times whatever is 0, so e to the power of 0 is still 1. So it's 1 minus 1 will be 0 regardless of what we started with, okay? Regardless of what k and m, except when k equals to m, and then it's different. But for any other, it's just becoming integer, some number, whole number, and whole number of 2 pi's is just you're doing whole number of rotations on that unit circle, you get to the same point, because 2 pi is full rotation, right? It's full angle. So 2 pi is practically 0 angle, right? So this is proof that inner product always equals to 0, which means vectors in their bases are orthogonal based on that definition, inner product, right? So we showed that this is the formula that you can use to compute the coefficients, if this is the case, if it is orthogonal. And for orthonormal, that v dual function, vk basis, will be exactly equal to v, right? So if basis is orthogonal, they are the same function up to a coefficient. If they are orthonormal, then they are exactly the same without coefficients, okay? So here the coefficient will be 1 divided by t, as we showed previous time, because you need to normalize it by norm square, if you remember, just to show you again that function. So this is the formula, okay? So that formula needs to be normalized by that thing, but if that thing is 1, then you get that formula. So we are using that formula now, and we get that kind of coefficient, which will be just for continuous time, it will be inner product with that function, which will be that thing divided by t. And for discrete time, practically the same thing, just sigma instead of integral. If you have discrete points and you're doing discrete Fourier series instead of continuous Fourier series, all right? So this function will be just that thing. And when you learn Fourier transform, people just give you, like lecturer probably just gave you that function, say like, well, use it to compute the coefficients, but this is where it comes from. Okay, this is the original idea, like where all of these things are coming from and why people are using specifically that function and not some other function, because it is orthogonal. It's very convenient as a basis for things, right? And as I said, it will be exactly equal without coefficients if it is orthonormal. Any questions on that? Okay, so here is, if you don't know how Fourier series look like, this is how it looks like. Just reminder, or maybe this is something new to you, how you represent something in frequency domain. Let's say you have some sort of function, which is periodic function like that. And this is very simple function, in that case, just sum of two sinusoidal waves. but it could be much more complicated. And typically you have infinite number of the sinusoidal waves to describe your repetitive function. But in that case, it's just two, all right? So to draw spectrum of that, which is amplitude spectrum here, you're just saying this is particular frequency, which will be ZF, and this will be like 3F frequency. So these are two sine waves. So it describes that in the plot as a function of frequency now. Instead of time domain, you convert it into frequency domain. And in frequency domain, that function will look like that. So you'll have some amplitude, which is how tall that thing is. This is a green bar at frequency F. You have no frequency 2F. You might have it, but you don't have for that particular signal, okay? And then you have 3F is smaller amplitude, so it's not as tall as the previous one, all right? This is how you describe spectrum of the signal. So higher the things are, higher the amplitude of these components. Farther to the right that thing is, faster the frequency, which means it's kind of changing much more frequently, higher frequencies, all right? And typically in regular signals, when you're doing Fourier transform, this is the kind of plot of you will get that you will get from Fourier transform or Fourier series. You'll have just spectral diagram and you'll have many, many, many bars in discrete time or continuous curve of frequency response for continuous case, continuous Fourier, all right? So this plot just tells you how much of each component, sinusoidal component in that signal you have. Let's say you have all these brain signals, which have all kinds of oscillations in them, and you have particular ranges of frequencies. So you might have that plot going up, having some peak in frequencies, which are stronger represented in the brain signal compared to other frequencies. So in that plot, which would be probably like almost continuous plot, you will have some peaks, valleys, and other things from which you can interpret how much of each frequency component you have in your signal. Like, do you have a lot of alpha oscillations or beta oscillations? Or maybe you have that 60 Hertz oscillation, which is line noise, which you typically see in all of the biomedical signals, and you want to remove it. So you'll say some kind of hump around 60 Hertz that you have line noise because these devices are recording all kind of line noise and other noises, wherever you record it, all right? So here's how it looks like. And sometimes you want to convert it also to angular frequency, which is called omega, and omega is just 2 pi f, 2 pi times frequency. So this is just omega and 3 omega. Whatever the frequency is just proportional to the frequency. So some people like it in omega, some people like it in hertz. Like omega is radian per second, instead just different units and rotations per second. All right, any questions on that? This is how you represent it in spectrum. Yeah, this is not the course to talk about signals too much, so I'm just jumping through what people might do with that, but yes.
Excuse me. I wonder why we just get amplitude at F and 3F and nothing between.
Because you have only two sinusoidal waves, which are components of that particular signal, okay? If the signal looks much more complicated, typically you have a lot of different components, infinite number of components for most of the signals. Like rectangular signal includes all of the odd frequencies, kind of sum of sines to write rectangular signal, to approximate rectangular signal. And you'll have infinite number of frequencies, obviously, in that signal. Because you'll have sine, smaller sine, smaller sine, smaller sine, and infinite number of them to add up to the actual rectangular wave. Because as you can see, sine waves do not have corners. So you need to add more and more higher frequencies to mimic those tiny, kind of very fast transients, okay, at the boundaries of the rectangular wave, when it switches to the step, right? So to model that kind of very strong slope, you need almost infinite frequency here, right? Because this frequency is kind of infinite. It jumps at 0 time from minus something to plus something. Okay, so you need very, very high frequencies. Now these frequencies will have like tiny components, tiny amplitudes, and you will correct it a little bit to match the exact shape. You'll add more and more of them to get closer and closer to that kind of shape. And only at infinity you will actually reach rectangular wave. So that's how it works. In that case, this particular wave is just sum of two sine waves. So you have only two frequency components. It's just for presentation purposes that you will see where frequency components are coming from. But in practice, you have infinite number of these bars typically. Okay, any other questions? Okay, another example. So here we have orthogonal basis, which is not exponent anymore, but sinc. And sinc is defined by sine of pi t divided by pi t. In math, sinc function is actually division of sine by t. It's like sine of t divided by t, but in engineering, we always define that with pi for convenience, because computations become much easier when you have sine of pi t divided by pi t instead of just t, right? So this is how we define sinc function. And this function is used as orthogonal basis, and I'm not proving that this is orthogonal. You can also do the same computation as on the board and do integral of one sinc times another sinc. And then you have multiplication of two sine functions divided by square of pi t, right? And then you integrate on that, it becomes a little bit complicated. You do that by parts. And after all that complicated computation, you get, regardless of what k and m are in that sinc function, you get 0. Okay, but for k equals to both of them, okay, k equals to m, you will get t, similar to just sine and cosine. Okay, similar to Fourier, to exponent. So you'll get practically the same norm to that sinc function, and you will get that orthogonal as well if you compute it. So the claim is that if signal is band limited, and band limited means that the highest frequencies that you have in that band is below particular threshold, so only lower frequencies present in that signal, you can reconstruct that signal completely from discrete points. So you sample that signal at particular interval, okay? And if you sample it with particular t sampling interval or f sampling frequency, okay, you can reconstruct it if that condition of omega larger than pi divided by t sampling is. Okay, so if this is your threshold for frequency. So all frequencies are lower than that omega, which means that magnitude, or not magnitude, spectrum of that signal above that omega is always 0. Okay, you don't have any frequencies above it. And this is what that thing says. Okay, so if your spectrum as a function of omega is 0 for any omega larger than that threshold, or that number is, and this is your sampling interval, okay, how fast you sample, then you can reconstruct the signal using the sinc functions. It's called Nyquist theorem, sampling theorem. Okay, same thing, you just represent that signal as a function of coefficients, okay, times this basis functions, which is whatever we did before with Fourier series. And magic, Sk is computed as inner product between these two functions, okay, which was exactly the same thing that we did before. This is exactly the inner product divided by t, because you need also to normalize it. This is how you compute coefficients, okay? So Sk is just inner product between this function and this function divided by norm of this function squared. T is norm squared, right? Same formula that we used before for Fourier series. But this is completely different thing. This is for sampling purposes, for reconstruction of signal from samples purposes, completely different theory. And it's called also angular Nyquist frequency. Who heard about Nyquist frequency? This is kind of a famous term. So Nyquist frequency, people just drop Nyquist frequency and saying like, well, you need to have frequencies up to half of the sampling frequency, right? This is what Nyquist frequency is. Nyquist frequency is half of the overall frequency band that you have. This is what Nyquist frequency is. So why is that thing somehow related to Nyquist frequency? Why is that thing is actually Nyquist frequency? It's just conversion to omega. If you remember, frequency is like 2 pi f is omega. It's just proportional to 2 pi. And this is how you get to that. So what you want to do, let me write it on the board to be easier. here. I will just copy that formula as it was there. So the formula is omega larger than y divided by ts. Okay, this is what we want to show. See it here. Interesting, this camera is recording only half the board. Have that omega Nyquist y divided by ts. And ts is sampling interval. Okay. So what do we know about that function? So Nyquist frequency. So Nyquist frequency is defined by sampling frequency, okay, which is half of it. There's 1/2 of sampling frequency. Okay. But what is sampling frequency? Sampling frequency is 1 divided by ts. Sampling interval. Frequency is 1 divided by interval. So you'll get that as 1 divided by twice ts. Right? So omega n should be 2 pi. That thing multiplied by 2 pi. This is how you convert frequency in hertz to omega in radian per second. Conversion of units. Right? So let's put it together. So we'll have 2 pi and f, which is 2 ts. 2 will cancel. It's pi divided by ts. You get the same thing as that formula. Okay, so practically speaking, saying that kind of thing is same thing as saying just Nyquist frequency. Right, so this is angular Nyquist frequency. Any questions on that?
Okay,
Yes.
a question about the integral.
Mhm.
The integral, is it from minus infinity to infinity or?
Integral is from minus infinity to infinity, yes. Like this is, if I'm not giving you any boundaries, it's default. Okay. Yeah, so it's like on entire scale, which means it goes to minus infinity and plus infinity, and then function looks like that. Have you seen sync function? How it looks like? The overall shape of it. That. Something like that. Now this is practically, these two formulas are basis for all sampling theory, which means everything you know about Nyquist, Shannon theorem, how to sample different signals, how you can reconstruct different signals from given sample points, assuming that they are band limited, which is typically not right thing to do because you almost never have band limited signals really, but sometimes you have it. So for that assumption, you can use that theorem to reconstruct from given discrete points, you can reconstruct any signal. You can reconstruct it exactly. It means you'll have exact continuous signal from discrete points, which sounds almost impossible if you're not thinking about that too much, right? Because like you have only a few points and anything can happen between these points. On the other hand, if you kind of making it dense enough, then you have less and less space to introduce all kind of big changes. So what happens is that these big changes are typically higher frequencies, right? So you need to jump faster between the points to make it not smooth, right? Between the points. And more points you have, faster you need to jump. So this makes more sense in that, like if you're thinking intuitively about that to destroy the perfect picture where you can reconstruct completely the entire signal, you actually need very high frequencies between the points to make all kind of zigzags somehow, right? And not just to connect them smoothly with particular function. So this is why you need broader band, more frequencies in the signal. And then you will have more troubles reconstructing the signal if it is not band limited, because it can jump whatever you want between the points and you don't know how, so you cannot reconstruct it, obviously. Okay? You'll have exactly the same points, but between the points could be anything. So this theorem states that if you have band limited signal, it can do only one possible thing between the sampling points. You have no other possibilities, only one possibility if you limit in the band, maximum frequency of your signal. That's it. And this is why before sampling, people always use low pass filter. Let's say you have continuous sensor which is measuring some signals, whatever they are. So you're measuring that signal. Before you're sampling that signal and discretizing that signal into computer kind of list of numbers, you always put low pass filter with Nyquist frequency in it to limit the band, that you will not have aliasing. It's called aliasing of signal, which means all of the leftovers of higher frequencies will kind of introduce all kind of weird artifacts, ringing artifacts into the signal itself back. That energy will be kind of reflected on other frequencies, which you don't want. So you will introduce additional artifacts by sampling itself. So you need to be very careful to filter it first with low pass filter, remove all of the higher frequencies above Nyquist, and only then sample. Right? So this is how it works. Any questions?